Well, it's because we can now show very directly the properties of the correlation that follow from it. So let's make a simple observation. Observe that if I look at the difference between the standardized value of x and the standardized value of y for an observation and I square it, that we have to get a number which is not negative. And so we can add those things up, and we now find that if we add all of those terms over I, then if we add those terms over I, we find that, of course, the sum of those squares has to also be greater than or equal to 0. Now we simply expand this expression and look at what we get when we do it. So we take the square term and we expand it with a sum over I. We have a sum of the squares of standardized values of x. The next term we get is a sum over I of the squares of the standardized values of y. And then we get minus twice the sum over I of the standardized value of x multiplied by the standardized value of y. And the exercise we've just been through here, because the standard deviation of these values, of these standardized values, is equal to 1, if we go and look at what's involved in the formula, we'll see that this just becomes n. All that's missing is the dividing by n in order to produce the standard deviation. I'm taking the square root. Similarly, this value here is also equal to n. But what have we got here? This is the question. If we look at this here, we see that in fact we have 2n times the correlation. So where did this come from? Because the correlation was the sum over I of xi minus x bar divided by sigma x times yi minus y bar divided by sigma y. And that is simply the sum over I. I've left out a 1 upon n here. It's simply the sum 1 upon n times the sum over I of x tilde I times y tilde I. Okay. So we have this very simple property here that this expression has to be greater than or equal to 0. So we follow that down. What do we actually have? We have 2n into 1 minus r. So what we have at this stage is that this expression is greater than or equal to 0. If we divide through by the 2n, it doesn't change anything. So what we find is that 1 minus r is greater than or equal to 0, and, or equivalently, that r is less than or equal to 1. So that proves the first fact that we were given about the properties of correlation, which is that the correlation must be less than or equal to 1. We can do exactly the same argument, and I encourage you to do it because there's nothing like doing it for yourself. But if you change this to a plus up here, you could track it through the entire argument, and down the bottom you will find that the correlation is greater than or equal to minus 1, if you do it correctly. So that's two of the key properties that we have about the correlation. We can, however, get from this one more thing quite easily, which is the fact that we only get a correlation which has magnitude 1 if there's a perfect straight line relationship. Because if we look here at how can the correlation be 1, the correlation can only be 1 here if we got 0 at this point. And so what we find is that r is equal to 1 if and only if the sum of the squares over I of the differences between the standardized values of the two variables is equal to 0. And the sum of squares of something can only be 0 if each of those items is itself 0. So the standardized value of x must equal the standardized value of y for each point, for each value of I. So in fact, when we go on to the standardized scale, we learn a lot about what's happening here. We get almost for nothing, we get to discover the core properties of correlation, which are that it lies between minus 1 and 1, and what's more, that we can only get a correlation of magnitude 1 if the points lie perfectly on a straight line. So I haven't made it clear why this shows that the points lie perfectly on a straight line, so I should do that for you. X tilde I equals y tilde I if and only if we have x minus x bar, xi minus x bar over sigma x equals yi minus y bar over sigma y. Now, I'm not going to do every detail in the process, But the point is that these values here, x bar and sigma x and y bar and sigma y, are not changing from point to point. So when we rearrange this, we can solve for an equation that gives a linear relationship between yi and xi with fixed coefficients that depend only on the means and standard deviations and the correlation. Okay. So that gives us many important properties. We can glean a little bit more about what's going on if we switch, instead of working algebraic like this, to looking at a picture and thinking about what the picture can tell us further about the process. Slide 6 shows our original data, but now the units on the axis are not in centimeters and kilograms, but both axes are in standard units. And what we see is that the origin now of the coordinate system is sitting in the middle of the point cloud. Absolutely spot in the middle. The vertical axis is dividing the points pretty much in half vertically, and the horizontal axis dividing the points pretty much in half horizontally. And now we can look at what happens to the standardized values in the 4 quadrants. We see that the majority of the points are in the top right quadrant. And for those points, the standardized value of both variables is positive. And when you multiply those two things together, we get a positive number. And remember, when we're computing the correlation in this process, we're multiplying standardized values together. So values from the top right quadrant are going to give us a positive contribution to calculating the correlation. If you look at the bottom left quadrant, see also that both standardized values will be negative, so when you multiply them together, you get a positive contribution. So the points from the bottom left quadrant will also tend to push the correlation upwards. There are very few points in this example which lie in either the top left or the bottom right quadrants. In those quadrants, you get a negative contribution. So depending on where the points lie in the quadrants is whether you get a correlation which is positive or whether it's negative. And the closer they lie to a straight line relationship, the more the points tend to lie all either in the top right and bottom left quadrants or in the top left and bottom right quadrants. The first giving you a correlation near 1, the second a correlation near -1. So a little just overlaying on top of the data, thinking about what's going on in standard units enables us to learn a little bit more about why it is that the correlation describes scatter plots of data in the way that we saw originally in the examples. Right, let's stop that bit. Right, we're nearly there, promise. I'm going to conclude this podcast by looking at what happens in regression if we do it in standard units, and we can see that it's actually very easy to derive the form of the regression line. Unlike other methods which rely on calculus, we don't need any complicated mathematics to do this. So in regression, we're going to use standard units and so our residual, the error for our prediction process, will be the difference between the true value yi, but it's in standard units, and the prediction we're making with the line that we're going to use here, alpha plus beta times the value of x, but again in standard units. And what do? We form the sum of the squares of these things. So we want to sum over I of ei squared. And so we expand out this process here. We get the sum over I of y tilde I squared. We get the sum of the square, we get this thing squared as well, so we get the sum over I of alpha plus beta x tilde I squared, and then we get minus twice the sum over I of y tilde I multiplied by alpha plus beta x tilde I. And we just continue to expand out here, and we get a slightly more elaborate looking expression, which gives us the sum over I of y tilde I squared. When we expand this out, we'll get an alpha squared, but we'll be summing over I, so we're going to get n copies of alpha squared. And then we're going to get the cross product term here. We'll get alpha beta twice with the sum of the x tilde i's. And finally, from that bracket, from expanding this out, we'll get beta squared times the sum over I of the x tilde squared there. And then we expand this piece out here. We get minus 2 times the sum over I of, there's an alpha here, to have the sum over I of y tilde I. And we also have minus 2 beta times the sum over I of x tilde I, y tilde I. Okay, and it looks like things are just getting messier as we go here, but actually we know about all of the things that we've got in this process. Right, so it looks in this process as though that we've made things worse, but in fact when we look closely at what's going on, we'll see that we know all of these quantities. So we can just replace them by things that we've already seen. We've seen that the sum of the squares of standardized values is just n. So we have n plus n alpha squared. This has not got a square in it at all, so this is basically going to be the average, well, the process of computing the average, so this is the sum of the standardized values, and that's always going to be 0, so that term will just disappear. This is going to be plus beta squared times the sum of the squares of standardized values, so that's again going to be an n. This term doesn't involve any squaring, so it disappears also. And finally, this is our friend here that involves the correlation. We have 2 beta times n times the correlation. And if we look closely at what we have here, we can see that it's always, if we try to make this whole expression small, there's no point in having a value of alpha that gives us a positive contribution here. We can immediately minimize by taking alpha equals 0. And so now we're left with the following expression. We have n plus into 1 plus beta squared minus 2 beta r. And we want to minimize this by choosing the value of beta. And we could differentiate and do it by calculus, but we don't actually need to do that because we can do it as follows. It's n, and then we have beta minus r squared, and that gives us the right amount of beta squared, the right amount of beta r. The only thing is it didn't give us the 1 here, so if we put a bracket in here, we get plus 1 minus r squared. And again, we can see that without doing any calculus, that we don't want this to be positive. It can only be positive or 0. We would like it to be 0. So that tells us that we should make the expression as small as possible by taking beta equals to r. So it turns out that regression is an incredibly simple story in standard units. The prediction in standard units for y is simply the correlation multiplied by the value of the x variable in standard units. And there's nothing else to it. It shows us what an important role the correlation plays in all this. And we can then put things back into our original units because we know how to go back through this process. So we can just complete it, and we'll see we get the usual formula. If we realize that the standardized value of the prediction is y hat minus y bar divided by sigma y, that has to be equal to the correlation multiplied by the standardized value of x, which is x minus x bar divided by sigma x. And if you go back through this entire process to where the regression equations are computed in the first place, you will find that this is exactly the same equation that you would start with. So what's the conclusion from all of this? Well, my conclusion is that it's helpful to do the mathematics, because the mathematics enables us not just to know the properties of correlation, but along the way tells us a great deal about what's fundamentally happening here. At the very end of this, the final thing we learn is that the key to understanding what's happening in both correlation and regression is to think about the plot of the data in standard units, where the origin, in fact, is sitting in the center of the data cloud, and you can see that which quadrants the points are falling into together. And from that, you can work out why the correlation is the way it is for a particular set of data.